Hello everyone, this is Mr. Underkoffler, and today we're going to be looking at proportional and non-proportional relationships. You can go ahead and follow along with me here as I read the beginning of the notes. It says a relationship is proportional if it has a constant ratio. Now what do I mean by constant ratio? I'm talking about where the ratio is always the same between its two quantities. Now, this might not make 100% sense yet, but when you start seeing today's problems, which are going to be shown in tables, you're going to see there's two quantities, two different types of values. And when there's a constant ratio, the ratio is always the same between those two quantities, then we have what is called a proportional relationship. Now, there are other names for constant ratio. Some of these names are going to be familiar. For example, the unit rate. We've talked about unit rate already. Unit rate is going to tie in to this lesson. Another phrase for constant ratio is the constant of proportionality, which is a very fancy sounding phrase, but it's one that you are going to hear throughout this unit. And then another phrase that could be the same as constant ratio is a constant multiplier. From the one quantity, which will be in the one row of the chart, to the other quantity, to the other row of the chart. You'll see what I mean here when we look at some examples. Starting with the examples, the first one we have here is the cost of coffee by the weight in pounds. Is there a constant ratio? Well, let's set up some fractions and divide. You can see I have this written over here on the side. We're going to be dividing in our calculator. So from the first column here, we have the weight of coffee as half of a pound, and we have $4.50. We know that when money is involved, the money will go in the numerator, so we divide 450 divided by half of a pound in our calculator, and we get 9 pounds, or sorry, not 9 pounds, $9 per pound. Now, the next row, we have $18 for 2 pounds. So we're going to set up that fraction and divide, and that's going to give us, again, $9 per pound. The next ratio, we have $31.50 divided by 3.5 pounds. And again, that gives us $9 per pound. And then finally, $36 divided by 4 pounds gives us $9 per pound. So you can see all the ratios are constant. They are always the same. So this is an example of a proportional relationship, like we saw at the top. If there is a constant ratio, the ratio is always the same between the two quantities, then we say it is a proportional relationship. So that's what we have here with this example. Now, how does this tie in with unit rate? Well, that 9 that we got every single time from dividing with our ratios is $9 per pound. That is a unit rate, as we had just learned in a previous packet of guided notes. All right, now here's what we can do with that unit rate. We can write the relationship from the table as an algebraic equation. If it's $9 per pound, the word per, as we learned earlier this year, means times. So $9 per pound mathematically means $9 times the pounds. So what you can do is, using some letters here for variables, C for the cost, W for the weight in pounds, $9 times the pounds would be $9 times the W, the weight in pounds. And what does that give us? That gives us the cost, which we used the variable C here to represent that. So here's an algebraic equation that represents the table we were just looking at. Let me show you how this makes sense. If you take the pounds times 9, you will get the cost. And that continues the work. 2 times 9 is 18. 3.5 times 9 is 31.50. 4 times 9 is 36. So that's what this equation is trying to show you, that if you take $9 times the weight in pounds, you will always get the cost. All right, let's look at another chart example. Now this one's a little bit different. Instead of being a horizontal chart going left to right, this is a vertical chart where we have a column for ounces for the one quantity and another column for the price for each of those ounces. All right, so we have price of peanuts by the weight in ounces. Is this a proportional relationship? What we're going to do is we're going to take the price for 4 ounces and we're going to set that up as a fraction. So 72 cents, again, when money's involved, money goes in the numerator, divided by 4 ounces. We'll use our calculator and we will get 18 cents per ounce. Well, what about the next cost? $2.16 for 12 ounces. Set up that fraction. Divide in your calculator. Again, we're dividing here. We're not using our fraction key. We're actually using the division key. 216 divided by 12 gives us 0.18. So again, it's still the same ratio. Will that continue to work? What about 288 for 16 ounces? If I divide there, again, using my calculator, I get 0.18. Finally, what about $5.04 for 28 ounces? If I divide in my calculator, I get 18 cents per ounce. So the ratio was always the same. It was always 18 cents per ounce. So by definition, since the ratios were constant, which means they're always the same, this is a proportional relationship. And like I just did on the previous example, I can take the unit rate of 18 cents per ounce and realize that means 18 cents times the ounces, and I can set up an equation. 18 cents times a variable, here I picked N for the number of ounces, will always equal the price of the peanuts. I'll use the variable capital P for the price. And if you look back at our chart, you will notice that if I always take the number of ounces times this 0.18, I will always get the price. You can check this in the calculator right now. 4 times 0.18 gives us 0.72. 12 times 0.18 would give you 2.16. This is what this equation is trying to show you, that 18 cents, 0.18, times the ounces will always equal the price of the peanuts. That continues to work time and time again in this chart. So, turning the page, if a relationship is a proportional relationship, then you can use its constant ratio, also known as the unit rate, and you can use that to express the relationship from the table as an equation. And that equation will always look, generically speaking, as y equals kx. Now here's what that means. Y is some variable officially called the dependent variable. It could be any letter that we choose to use to make sense. And it's going to be the unit rate. That unit rate we're going to generically call as k here in this generic format. And it can be multiplied times some other variable, which is officially called the independent variable. And that's going to be any letter that makes sense to choose for that. So this is what we just had on our previous two examples. On the first example, it was the cost equals $9 times the weight of the coffee in pounds. And on the example that we had secondly, from the first page, we had the price of the peanuts equals 18 cents times the number of ounces. So it's always going to be a variable equals the unit rate times another variable. That's what this y equals kx is trying to tell you. However, if a relationship is non-proportional, now how could it be non-proportional? If I give you a table of values where the ratios are not constant, meaning they're not the same, then that means that's going to be non-proportional. And when it's non-proportional, you cannot express the table of values using this type of equation that I was showing you, where it's some variable equals the unit rate times another variable. Let's look at an example of that. Here we have the distance traveled during a period of time. Will this give us a constant ratio if I take the miles and divide by the hours? Well, let's check this out. 50 divided by 1 would be 50. But is 70 divided by 2 also 50? Nope, that would be 35 miles per hour. Is 90 miles divided by 3 hours going to give me the same ratio? Nope, it's a different ratio, 30 miles per hour. And lastly, if I take 110 divided by 4, I would get 27.5 miles per hour. As you can see here, there is not a constant ratio. These ratios are not the same. So that means we have a non-proportional relationship. And we would not be able to represent this table using a simple type of equation like we did in the other problems, like 9 times W equals C or 0.18 times N equals P. That type of equation is not going to work when it's a non-proportional relationship because there's not a consistent unit rate. There's not. Let me tell you something. Even if the first 2 or 3 ratios are the same and the last one is not the same, that still would not be good enough to call it a proportional relationship. That would still be non-proportional. So non-proportional is not just when every ratio is different. If any of these ratios are different than the others, that's a non-proportional relationship. All right, let's have you try some problems on your own. You've already seen 3 examples done for you where the first 2 were proportional because the ratio was always the same, but the last one was not because when we divided, the ratios were different. So you're going to try numbers 1, 2, and 3 on your own. The directions say, state whether the relationship shown in each table is proportional or non-proportional. Now you need to show the work. I want to see the fractions that you are setting up, just like I did on the previous problems. Show me what fractions you are setting up and the answers you get from dividing in your calculator. Show me that work. If it is proportional, then you're going to write an algebraic equation that represents the relationship, just like we did on the problems from the first page, where we had the unit rate, something per something, and that means times the one variable will then equal the other variable. So you're going to write an equation if it's a proportional relationship. All right, as always with my videos, whenever there's independent practice, I need you to hit pause at this moment and try 1, 2, and 3 on your own. When you're done, then you'll hit play to see how you did. All right, did you already try 1, 2, and 3 on your own? If not, please hit pause now. Try these problems on your own. Make sure you're showing the work. All right, I'm going to start going over them. I hope you've already done these on your own. Problem number 1. We're going to take the feet and we're going to divide by the seconds, so that way we get feet per second. So that's 92 divided by 8, 115 divided by 10, 138 divided by 12, and 161 divided by 14. 92 divided by 8 gives you 11.5. 115 divided by 10, 11.5. 138 divided by 12, 11.5. So we are noticing this is always giving us 11.5. What does that really mean? The feet were in the numerator, the seconds were in the denominator, so that's 11.5 feet per second. So this is a proportional relationship because the ratio was always the same. And now we're going to take the meaning of the word per. Per second means times the seconds. So the equation that we could set up for this is 11.5 per second times the second. So that can be 11.5 times s. What does that equal? Well, that equals the feet. Now, you can pick any letters you want here. I picked S for seconds and F for feet. Maybe you want to say the seconds is a generic measure of time, so you could use T for the time in seconds, and F in feet is a specific measure for the distance that we're traveling, so you could choose D for distance in feet. Totally up to you what variables you want to choose, but you should have 11.5 times whatever variable you picked for the time in seconds equals the distance for the feet. All right, what about problem number 2? Set up our ratios with the money on top and the number of sales in the denominator. So that's going to give you these fractions that you see right here on my screen. If you divide the first one, you're going to get 75. You divide the second one, you're not going to get 75. It's 70.83 repeating. The third one gives you something different. The fourth one gives you something different. And by the way, you do not need to write out all of these places of the decimal. You don't have to. The point is to show the work, to figure out if it's proportional or non-proportional. Since the ratios are different, this is a non-proportional relationship. And unlike number 1, where we were able to write an equation, problem number 2, we cannot write that simple y equals kx type of equation for a non-proportional relationship. All right, problem number 3. This one, it's a little bit trickier to know how to set up your fractions. We know when money's involved, money's going to go on top. We know when there's a unit of time involved, like seconds, that normally goes in the denominator. But problem number 3, centimeters and inches, I mean, you could really set this up either way. I'm going to assume that you guys are putting the second row of numbers in your numerator and the first row of numbers in your denominator, because that's typically seems to be the way that we set these up with most of these table problems. But if you did it the other way, it's okay. Doing it this way, you're going to get 2.54 every single time that you divide. So this is a proportional relationship. The equation, this means 2.54 times the inches to give you the centimeters. So make sure you have the variables at the right spot. We're not taking 2.54 times the centimeters. We're taking 2.54 times the inches to get the distance in centimeters. So that's why the inches needs to be the variable that is multiplied to 2.54 to then equal the unit of centimeters, the distance in centimeters. All right. The next page is a little introduction to graphing proportional relationships. Now, you might remember from 6th grade math that an ordered pair is a point that we graph, and the coordinates of that ordered pair are always in this form. The first number is called the x, the second number is called the y. The x tells you how far you're going to go right or left. If it's positive, you'll go to the right. If it's negative, you go to the left. The y is the variable that tells you how much you're going to go up or down, where if it's up, you go positive. If it's down, that's a negative number. You might recall this is from an x and y axis. Again, x is going right or left. Y is going up or down. We will graph our points, actual points that we would graph on a coordinate plane, the x and y axis. All right, problem number 1 I've already done for you. We're going to take the previous examples that we had that were proportional relationships. So this is only going to be problem number 1 and problem number 3, because problem number 2 was non-proportional, which we could graph, but I want to show you something special about the proportional relationships. The first row is going to be the x's, the second row is going to be the y's, so that's going to give us 4 ordered pairs. Each column is an ordered pair, so 8 and 92 is the first ordered pair, 10 and 115 is the second ordered pair, 12 and 138 is the third ordered pair, and finally 14 and 161 is the fourth ordered pair. You can see I've already typed these up for you. First number is the x, second number is the y. And what I can do then is I can then graph this on an x and y axis on the coordinate plane. So for 892, I would go right 8, up 92. Now this was a little tricky. I had to realize that 92, halfway between 80 and 100 would be 90. So I want to go a little bit higher than that to get to 92. So that's how I knew how high to go for that dot. Next, for 10 and 115. Well, I know halfway in between would be 110. So I need to go between that 110 mark and the 120 mark to get to 115. So I'm kind of guesstimating how high to go for that dot. Next one is 12 and 138, so I go right 12. Where's 138? It would be just below the 140 mark. Just below it would be 138. And then finally, for the fourth ordered pair, 14 to the right, 161. That means I go up to 160 and just a hair higher for 161 is where I put that fourth dot. Now, here's what's cool about this. These 4 points would form a straight line, and if you continue to draw that straight line from where it begins, it would actually go through 0, 0, which is quite fascinating. Will problem number 3's proportional relationship do the same thing? Well, I want you to graph number 3 on your own. So again, we're going to have 4 ordered pairs. The first ordered pair is the 2 with the 5.08. So that's your x and your y. The second ordered pair is the 3 with the 7.62. So that's your x and your y. So you're going to have 4 ordered pairs. Graph each of them as dots. And will it form a line? Well, I want you to try that on your own. So hit pause on the video. Graph number 3's proportional relationship on your own. And when you're done, hit play to see how you did. All right. Did you already graph these 4 ordered pairs? Let's find out. Now I'm going to go ahead and move this chart down so that way it's going to be a little bit easier to see when I graph these what numbers I was looking at. Okay, so 2 and 5.08. I go right 2, up 5, a little bit higher, so that's where the 5.08 mark is. 3 and 7.62, so I go right 3, up 7, and where's the 0.62? Well, 7 is halfway in between. I need to go a little bit closer to the 8, so that's somewhere around there. 4 and 10.16, so go right 4, up 10, and a little smidgen higher for 10.16. And then finally 5 and 12.7. Well, 12.7 is a little bit lower than 13. 13 is the halfway point between 12 and 14, so I'm going to go a little bit lower than that. Will they form a straight line? Well, actually, yes, they will. And notice, once again, this is going through the origin, the point which we call 0, 0. That is the origin. So here's what I want you to notice, and you can get your pencils in your hand and write this down. The graph of a proportional relationship appears to always form a straight line that passes through the origin. When I say the origin, I'm talking about the ordered pair known as 0, 0. So quickly hit pause if you need to. Write those words in the blank. That's where we're going to finish this video for the first half of the guided notes. The remaining pages we're going to do in a separate video. So thank you for watching this one. We'll see you next time.